Okay, so our next speaker is Felipe Llanes.
I'll take from here, thanks. Okay. So I'm a local, I'm here for the diversity talk this afternoon, and I'm going to speak about changing the particle number on a quantum computer, and that's the work of my grad student here, Juanjo Galvez. Here you have him in a state of spin up. So anyway, if you have any more questions after the talk, you can reach me or reach Juanjo, who's sitting out here. Right, so the talk is way too long. I'm going to see what I can shorten. But let's go over the foreword, which will explain you in 4 points how a quantum computing calculation runs. First, you choose the codification of the states of your system, and you initiate the quantum computing memory to some psi of 0 there. Then you decompose unitary operators into elementary gates and evolve the state. And finally, you measure some expectation values. So it's similar to a lattice gate theory computation, but it runs on sheets, on foliation, advancing with time. Okay? So in this talk, I'm not, unlike lattice field theory formulated on a quantum computer, I'm not going to be using the Kogut-Susskind formulation, if you know what that is. What I'm going to do is follow more closely the particle physics way of thinking. So I'm going to get stuck with canonical quantization in terms of particles in momentum space and not proceed to fields in position space. Okay? Now, simple calculations are already running in quantum computers. They're not particularly strong. This is a graduating kid here, and he used the Cornell potential to recompute these heavy baryons, which are some of the most interesting particles in the standard model. I haven't shown up yet. You know, there's an entire nuclear physics out there made of heavy quarks. Anyway, so he recomputed this and got similar results to the literature. This is a computation that you can probably do with a hand calculator and a bit of patience, and definitely with your laptop. Yep. The quantum circuit is something like that. You have to prepare a state, which is down here. So it has some rotations, it's a variational state, some entanglements with CNOT gates. And then once the state is prepared, you insert the Hamiltonian of the Cornell potential, so you need the matrix elements of that thing in that state. And then you make a measurement up here at the top. And that's going on. Okay, so you can do with 4 qubits. This was possible already a couple of years ago. Now, we're being a bit more ambitious here, and we're trying to go into field theory and encoding particles. So the first thing we need is a representation of a particle, right? So for this, we use a register representation. You get a bunch of qubits, each box here is 1, and the first thing you do is get a qubit telling you whether the particle is or is not there. Once you decide that, you can add color. For 3 colors, it's enough to have 2 qubits. Then spin, because here you have an extra state with 2 qubits, you can decide whether you're talking of a particle or an antiparticle, if necessary, if you're dealing with fermions. Flavor, if you need to, and the rest goes to discretize momentum. Okay? So this unit of memory is basically 1 particle in the quantum computer. All right? Now, if you count, you need about 15 qubits per quark to do that. So we're already in business for quark model size computations because the Eagle chips that IBM has in the public domain are 127 qubits. You can run on those. So simple calculations can work already. Now, the canonical operators, which is really what I wanted to talk about today. So we want to implement canonical commutation relations or anti-commutation relations. From there you can get a Fock space and so on. And the way of thinking about this is like the constructor and destructor methods in object programming. So we want these objects to add something to a register or take it off. Okay? So here is the implementation in 1 register. We put here 3 of those, and then the 4th is empty. And we might want to either eliminate the particle on the 3rd or create a particle on the 4th. Yes? So this has several pieces. The first thing is some projectors that need to decide how many registers are full and how many registers are empty. That is, where am I going to put the next particle created in the memory? All right, so once we have that, in that slot, we can create the particle. So we have some lower level operators here. And these are a set scrap operators for the quantum numbers, erase or write in the memory. And then some control operators. Why do you need that? Because in usual computer programming, you use control expressions like if, then, or else switch, and switch case, and so on. But in quantum computing, what you're doing is multiplying matrices one after the other. Okay? So everything is done by multiplication. So you need to implement this logic in terms of multiplication, and that's what these operators do. So if there is a 0 in the register and you want to continue having 0, this would act. This would denote that there's a particle and there continues to be a particle. This goes from 0 to 1. And then if they're acting not on these states, so if 1 acts on 0, it should give 0. Oops, 0. But there's no 0 in a quantum computer. The state vector is always there. Yes? So what do we do with that? Well, happily, everything is going to be exponentiated because we're going to be using unitary operators. So the stuff in the algebra will go up in the exponent and the identity will rescue the day. Okay? Right. So, for example, these projectors can be constructed from the lower bricks, the control operators. Well, Juan has generated a formula for all this. And the most difficult piece next is the symmetry. If you have two particles and you have a third one, you want to end up in a completely symmetric or anti-symmetric state depending on your quantum statistics. Okay? So this is the step anti-symmetrizer. You add the last particle and you want it to be symmetrized with all the others. But you want to do this in a relatively cheap way in terms of gate cost. So we do a step symmetrizer or anti-symmetrizer, which is we only symmetrize the new particle with the n-1 that were already in the memory, that were supposed to be already in an adequate quantum state with the correct symmetry. And then it's an operation of order n, with n permutations, basically. So it's relatively straightforward. All right? Once we have this creator operator for a register, we can sum over all the registers, and we have the implementation in the computer of the canonical operator, which, if there is nothing in the memory, it will create the first particle here. If there is one particle, it will create it in the second register. If there are two in the memory, it will create it on the third register, and so on. Very good. This is what we would like to have, canonical commutation relations, and anti-commutation relations. No? Right, but what happens if you have a full memory? So you can calculate easily with those operators that I compose the commutation relations, and you get a canonical term with a delta, some projectors. But then, if the memory is full, if you're going, if you have a finite memory and the nth register is occupied, you get an extra term. So there's a boundary term, and this is typical of lattice computations. You have boundary terms when you reach the ends of your momentum grid or whatever. So here there is a boundary term when you reach a full occupation, which has to be removed by systematically increasing the memory and seeing how things change. There'll be some renormalization group type work here to do. Okay. For example, you can do number operators and so on, and the number operator acting on a state which contains j particles will give you the j's, j multiplying the same state. So you can check that the usual algebra works with this setup. Well, now you can go for a Hamiltonian. Let me skip this part, is a bit technical, and I'll speak a moment about evolution operators. So, for example, the free evolution, U11, would be the exponential of the energy and then the number operator, basically. So we have constructed this in terms of lower level objects, so now it's a matter of accumulating this phase. One advantage of that is that, for example, if you want to add a chemical potential, because you want to work in heavy ion collisions or in neutron stars or something, in this formulation it's trivial. This is something that in lattice gauge theory it's terribly difficult. So there are small niches of work where this quantum computer formulation would be very useful. Okay? Right, so here is the free evolution operator in terms of the beasts that I have constructed in the talk, and this U11, which is the self-energy of one particle. Okay, so here we have one particle jumping some quantum gates, and that's how it looks, quantum computer diagram. So you see that the gates act independently on each of the register. Each thick line is a register, and you have a line acting on it. Just like in a Feynman diagram, you have a self-energy acting alone on one particle. So this is equivalent. Okay? And then you can accumulate the phases somewhere. For example, in the presence-absence qubit, you get all these registers. Each one will have a momentum, and you can use them to control and sum up the energies of all the particles in this last qubit where you can eventually read it and know what's happening in the system in free evolution. All right, so now let's get some additional Feynman diagrams in which you have particle creation, momentum exchange, whatever. So I'm going to look at something with momentum exchange and something with particle creation. So the Hamiltonian is a sum of pieces, so you would like to factorize this, the unitary operator that is a product of gates, but that's unfortunately not possible because of the Baker-Campbell-Hausdorff rule. If you have exponents that don't commute, this is not a simple product. This is what we have, this is what we want, and the two things are different. Okay? But there is something called the Trotter decomposition, which tells you that the limit of a product of these exponentials to the R power is the exponential of the total Hamiltonian. But this is a limit. So again, this is like lattice gauge theory. You have here some parameter whose limit you have to take to infinity, like say the continuum limit or the infinite volume limit in lattice gauge theory. Well, if you discretize, you have an error that you have to pay, and there is something called the Trotter expansion that does exactly this. The small parameter is the time divided by R, the number of steps, delta t, basically. For a second, let me compare this Trotter expansion with the Born series that we use to formulate usually perturbation theory in quantum field theory. Yes? So the Born series goes as interaction, propagator, and so on. This Trotter series is rather interaction, free Hamiltonian, maybe another interaction, free Hamiltonian. So it doesn't have the convergence problems of the Born series at low energies. Okay? Right, so you can now codify in code momentum exchanges when two particles collide, and the circuit would look something like that, in which now the unitary gates, this abstraction, well, touches two registers, and there is a formula for them in terms of the lower level bits that I described at the beginning. If you have a particle splitting in which you emit a lamp, well, both particle momentum and particle number change, and then things are a bit more complicated. You have symmetrizers, then exchange operators, then you have the gate that creates a new particle. There is a lot of extra work because you have to decide whether the particle is going to violate the Pauli exclusion principle by there being another one with the same momentum in the memory. And everything has to be properly symmetrized at the end. So there is some number of gates. And I guess this is the formula for the splitting. So a gluon becomes two gluons, will be something like that. Okay? All right, so this has to be coded, and it needs a few exchange and swap gates. And I guess I better be finishing. So the most important conclusion is that this can be done, okay? Because all the calculations go in polynomial time. If you go over the table, for example, this is U11, the free evolution. You wouldn't expect that to give much trouble in terms of computing time. It scales as the number of particles times the number of momenta that you want to encode in the lattice, okay? Now let's see a more difficult one. This U21, some splitting operator. Well, this goes as number of bosons, number of fermion squares. So this is a fermion spitting out a boson. So in total you have a cubed scaling here, then the number of momenta squared, and then a logarithm, which is polynomial, right? No exponentials. Now this happens because the Hamiltonian of gauge theories, in Weil gauge or simple theories which have only a few particles in every vertex, typically renormalizable theories, are local. So they don't have every particle interacting with every particle. So that helps a lot, and it means that the complexity of this is within something that can be calculated. Okay? So what we're doing now is putting these operators in Weil gauge for chromodynamics. That's going to entertain us for the next 6 months. Okay? So if you have any questions.
I have a very basic question. What can you calculate with this? What couldn't be calculated before? Or what do you try to improve?
Okay, so plan. The next move I'm doing is sending Juanjo to Argonne National Laboratory, where he's going to try to look at fragmentation functions. Okay, fragmentation functions can be extracted from data, but to date cannot be calculated. So that's something that long-term might work. And lattice gauge theory has trouble with that. Another thing is finite density. If you add a chemical potential, you have a sign problem in lattice gauge theory. Here it's trivial. If you get everything working, you have your own set of problems to solve, but not that one. So there are niches where things, might make progress.
Okay, and this kind of, let's say, practical applications, when do you think you can get there?
Which you cannot do with a conventional computer.
When?
Yes, but the ones that you cannot do with a conventional computer, because the other ones you're already doing. I showed you a quark model calculation that is already done. But you can do that in a laptop. So you want things that cannot be done on a conventional computer, and I put that at a decade, which is less than 40 years. We always said everything is 40 years away. No, this is a decade now.
Yes, to do it for the color of the quark is fine, but not for rules.
Right. Yeah. When you're in an octet representation. Sure.
The question is sort of similar to that of the space because for the moment, the kind of computations that you can do with a quantum computer are very limited. In most of the cases, you can do reasonable things on the simulators, and the simulators have a limit of 32 qubits. So my question is, are you planning to make
maybe I went too quickly over this, but we have 127 qubit chips available.
They are available, but if you try to run this kind of algorithm,
not yet. We haven't run it yet.
You just get noise because the quantum computers are not working properly. So first, you need to make a proof of concept with a simulator which is error-free, and then you might try to do something in a real quantum computer.
Sure.
For the moment, you will not get much on a real device.
Too many swaps.
Too many swaps, too many decorators, too many quantum gates, and so on.
Yeah, well, our impression so far is that things are kind of working. Let's see how.
With limitations.
So I give 10 years. 10 years.
It's nice to do this kind of applications.
Any other comments? Okay, let's thank you.
Okay.